Divide out vector b. So make a point, what's never going in that denominator? Vectors. Now you will never ever do vectors in a denominator.
But he can divide the magnitude of both the vectors. Right?
That's right. Magnitude he's mentioning scalar.
Yes.
I'm looking for one, I want to find the one that could trick you. I don't want to trick you. Which one? I want 12.3, number 1 is good practice in the book. Those answers in the back of the book. 12.4, number 13, I'm so happy on because they're odd problems, so the answers are where? Back of the book. So when you're doing the ones on the practice set, you're unsure. Like if you're confident, you probably won't have to check these. But if you're unsure, go check some of these. I'm trying to find, I don't think I can stump you, but I'm going to try to. Okay. I just don't think I can do it. How about this? Vector, scalar, or meaningless? Some of you are probably pretty fast too.
Vector.
B and C are
That's a
vectors.
dot too. I should
Scalar.
be. I want to make sure when I make that dot, I want to make it big so you know it's a
But
dot.
B and C are vectors.
So that's a vector. That's a vector. Vector dot vector is a.
Scalar.
Okay.
That had meaning. That would have meaning, right? I'm trying to think of another one too. How about magnitude of vector A times, so when I put magnitude on it, and then here I got a vector B cross a vector C. Now hopefully you'll find this also has some meaning.
That's a vector.
Because, very good, that's a what?
Vector.
That's a vector. But what am I multiplying to the vector?
Scalar.
Some
Yeah.
scalar number, like an example like this. And if you multiply a scalar value, just not a dot product, just a scalar multiplied to a vector, then the overriding answer should be a what?
Vector.
You got it.
Change the magnitude.
You got it. And if you any doubt, just check the book for some of those for practice. Because I did put a few of those in there, didn't I? They make you think. I like that. That's good. All right, in your notes, put 12.5. Look at them all. I'm looking through here, nothing else weird. Cross products, dot products. So cool. We find area triangles. I love when you all are talking about those angles, or you brought up the point about angles, Art. I mean, this opens a whole new part of mathematics where it makes it easy to determine angles. Before it was all about what? Ooh, should I do the law of cosines or the law of sines? Should I get my right triangle? Man, now it's easy and you got two options. Sometimes you might go, which one should I use? I'll tell everyone if I have to find an angle, the book problem is find an angle, I always use this one. Just me personally, I think dot products are easier than cross products. So I just want to let you know that. When they ask me to find an angle, find the measure of the angle between these vectors. I always go for that theorem.
It's faster.
It's faster. I just find it faster to do a dot product than a cross product. Maybe a minute faster, but faster, right? All right. This is lines and planes. We're going to start with lines. And they call them the parametric equations of a line.
Is this 12.5?
And this is 12.5. Don't I care if I erase all that? Yeah, we won't need that. I mean, cross product will come up in our discussion. You bet. That stuff's going to be useful here. The parametric equation of a line. Wait, two-dimensional space. Isn't that the equation of a line? Yeah, you need a point and a slope. We get it. Y equals mx plus b. It's funny, in three-dimensional space, it's going to look kind of goofy when we try to write it this way. It really will. Now, it's not hard. It's just we do it in a different manner. We use parametric equations. We use parametric equations, all right, to describe that line going through space. What is parametric equations? We use a parameter. You go, what's a parameter?
Yeah,
A parameter is just a letter.
Yeah,
It's just a variable. We just use another letter other than x and y and what? Z. So, popular letter they like to use lowercase t. All right? That's the parameter we're going to use, t. Of course, you could have used I wouldn't use j or k because of the idea of ij's and k's. You know, you could have used like a what? Maybe a g or something, but we always use t. So, well, let's make up a point. How about the point 1, 2, 3? And when it's on some line in space, it's the point 1, 2, 3. The key is you need to have a parallel vector. That's essential. So when I'm going to run a vector that runs parallel to the line, and I'm just going to make it up. The parallel vector, I'm just making this up, everyone, is the vector 4, 5, 6. That's my parallel vector to the line. It runs parallel to the line. That's what you need to come up with your parametric equation of line. No question about it. No question about it. When we always need one point, just one point on the line. That's all. But you also need a parallel vector. A vector that is somehow parallel to the line. Okay? Now, have I provided that for you in this example? All right. Then here comes the parametric equation of the line. You could write this vertically, or you could write it horizontally. I think I'll write it vertically. Put your point down. X equals, put the 1 there, the 2 there, and the 3 there. Put a plus and a plus and a plus. I'm putting that parameter down T. Put a T and a T and a T, and leave some space. In front of these T's, everyone, I need you to put the parallel vector. So I'm going to draw an arrow right there. Right in front of these, the coefficients to these T's must be your parallel vector. And this will be your parametric equations line. So what goes here?
4, 5, 6.
There's the answer. You can put a box around it. Now, I wrote this vertically, right? Can you write it horizontally? Sure. What would it look like? My answer, x equals 1 plus the what?
14.
You can put a comma. Y equals 2 plus the
5t.
5t. Put a comma. And z equals what? So when you, because I need all of this to describe that one line. Now I know you're all like, why can't we write it like y equals mx plus b? Oh, I'll do it with you. I just don't think you're going to do it too often.
So these
You're going to leave it like
So
this.
the parallel vector can't be, the vector can't fall on the line?
It absolutely can fall on the line. I love that. And when that's going to be useful in most cases. And when it just has to be parallel. So you're like, well, could it be a vector sitting right on the line? Absolutely. But when they give you certain information, think like that. Go, if it's a vector on the line, oh yeah, I can use that. Because that's going to be the missing part. They're going to give you like some scenario. Hey, find the parametric equation line. Your key is you got to pick one of the points, doesn't matter which one, and then you need your parallel vector. Sound cool?
now this equation is for which one? The parallel vector or the line?
This right here describes the line.
Line. Okay.
And it goes on infinitely.
Okay.
You all agree that the line never stops, does it? So this is now, I want to point out, you go, I have just described this line in three-dimensional space. Now, how many points do you think are on that line? I love it. She goes, infinite. I love how she said that. Do you all agree? Now, I gave you one, but how many points are on this line? Infinite amount. Can we find like 3 of them real quick? Sure, let's make a little table. You want to find some more points on a line? What are some more points on a line? Well, let me put one of them. I could plug in anything for t. T is the parameter, right? It's just a variable. You get to make up any t values you want. Like for instance, what if t equals 0? It's just a parameter. What if t is 0? What's the point on that line?
1, 2, 3.
Oh, the point I gave you. Isn't that cool? So did you all see that? T equals 0 is the point that you had. But let's find some more points on this line. Just 2 more. Want to use t equals 1? What's another point on that line?
So that's 5.
Yep.
And 5 plus 2.
7 and...
9.
Can you find one more point? Hey, by the way, I'm plugging in easy integers, but could you plug in like pi? There's an infinite amount of points, but I'll use 2.
Thanks.
9,
9,
10, 12,
12,
15.
15.
15, yep.
Hey, could you plug in a negative value?
Yep.
I should show that just in case people thought you always had to use positive numbers for your parameter. Oh no. Use negative 100. What's 1 minus 4? 2 minus 15. No, wait a minute, I'm sorry. 2 minus 5.
-6.
And then 3 minus 6. Ooh, cool. They're all what? Hey, that was neat. That'd be the point. These are points. Hey, go on, bro. Isn't that awesome? Now, there's another way to write this. I wrote it what? vertically. I wrote horizontally. Isn't that your call? It really is. It's your call. Sometimes on a test, I put a blank space here. When you take that test, a couple weeks from now, and I go, find the parametric equation of the line. And I leave this long space. All the time, students just go off to the right and they go, they put them all right here. They write it just like this. Because that's the way they're doing their homework problems. They're like, I'm not going to fill out your whole stupid space. I'm just going to put it right here. That's totally fine. You can also write this as a vector. Isn't that neat? You can describe a line. This is the parametric equation of a line. You could describe it with a vector. So I want to show you that. Can you write the vector equation of a line? I'll put it right underneath this. What would be the vector equation that represents the line? Well, then what would I have to put in all my three components? I bet you know. Everyone look, I'm making a vector. Now we got to call the vector something. What do you want to call it?
The V.
Okay, V. We'll call it vector V, just to make up a letter for the vector. But this vector is going to describe this line. What's going to be the x component?
Oh, so 1 plus 4t.
Boom! What's this component?
2 plus 5t. And 3 plus 6t.
And if you want everyone, you don't have to do this. Maybe underneath this, you could lightly write that this is my x component. That's why that's x, right? Lightly. What's this? I want to write it really light so you always know, yeah, you're x. You're y. Y is equal to you. And this component is what? Sometimes students have trouble between x, y, and z in this t. You go, well, that's the x component. That's the y component. So can you write it like that? Mm-hmm. Sure. Now I wrote v equals, you know in math when we wrote f of x as a function? Well, in chapter 13 next week, we do something called vector functions. So if you want, since the parameter, the variable was t, you could also call this v of t. I'm just going to write that, if you want to do that. They don't show that notation until chapter 13. Might as well talk about it now. Can I write it as a function? Yeah, it's a vector. And what's the variable t? V of t. T is my one variable.
We did a little bit on calc too, just to
Yeah,
the graph and all.
that's right. Hey, as the third way, and when the third way is showing you how to write it like what? This. Now, it's going to look weird. So I want to give you a heads up. It's going to look kind of goofy. So maybe once, twice, you might write it like this, but you might stop. That was easy in what? Two-dimensional space. One equal sign with what? And was there any parameters in there? No, were there any t's in there? Let me make up an example. And that's two space, right? Line in two space. Why? Because the slope is 2. See, this thing will still have a slope. Y slope of 2, y-intercept 3, and all that stuff. Can we do that with this? Yes, that would mean we would have to eliminate what letter?
T.
The T.
T.
But it's going to look funny. So when you ready? They call these the symmetric equations of the line. I just don't know how much you're going to like this. I don't. 99% of the problems we're going to do are in vector form or in just that parametric form. And what would be the symmetric equations of the line? Let me just put this in quotations. This means we're going to eliminate what variable?
T.
The t. We're just going to get the t out of that thing. Can you do it? Oh yeah, but it
So-
looks fun.
Like 1 plus 4y.
Well, here's what we got to do. Everyone, if I want to eliminate the t, I'm going to need this one. I need you to solve for t. If I'm going to eliminate the t, then you know what I have to do? I'm going to solve for t in each case and set them equal to each other. That's all I'm going to do. Solve for t, solve for t, solve for t, and throw them all equal to each other.
So x minus 1 divided by 4.
All right, let me start out. X minus 1 divided by 4. Be solve for t here. Now I need you to do it here.
Y minus 2 divided by 5.
Okay, but you have to do it one more time. That's why this is kind of silly.
Z minus 3 divided by 6.
Look what I'm writing. Z minus 3 divided by what? I mean, what do y'all think? Yeah, it's just, follow me? This is much better to deal with parametric form. That's exactly how you'd write it, and you'd leave it like this. You'll see this, and if you check through the textbook, I want to make sure I at least signed one problem where it said what? Find the symmetric equation of the line. I just want to let you know that on my test, you don't have to provide the answer in the symmetric formation. Unless you really like it. Then you're gonna make me do all my math and go, is that right?
That's too much work.
Yeah, plus it looks funny, doesn't it?
Yeah.
And this is not very convenient for doing math integrals. We're gonna still do calculus in this, integrals, derivatives, it's just not, it's not very convenient. We're here, everyone, can you differentiate that with respect to t? Pretty quick.
Yep.
Just 4, right? I'm serious. You go, oh, then, but it is a way to eliminate the t. Isn't that funny? So maybe they should teach it like this way in Algebra 1 class, right? When students just get students used to this? I don't know. That'd be, up for an argument. People, nah, you don't need the t yet. All right, great job with that. So let me throw a problem at you and see if you can do this. Hey Maggie, we just pick a point in space. Anything. Make one at least negative.
5, -2, 8.
All right, everyone, here's a point. There's a point in space. I'm picking the next point. It's 7, 1, 12. Another point in space. I need you to find the parametric equations of that line. That's what I need. We say to ourselves, wait, what do we need? We need a point, and we need a parallel vector.
So,
Well, we got 2 points. Does it matter which point we use? No, I'm going to use Maggie's. Doesn't matter though, you agree? We just need 1 point. I'll use that one. But I'm drawing a picture because I'm blanked. I didn't give myself the parallel vector. So I'm just going to draw a picture. Drawing pictures makes me think better. Maybe drawing a picture helps me think. 5, -2, 8. What was another point on the line? But I'm stumped on one because I know to get my answer, I do have to provide a parallel vector. Any suggestions? Watch this. What vector can I use? It's got to be a vector that's parallel.
Tip minus tail.
He says use that vector right there. Just make it. Wouldn't the vector right on this line, tip minus tail, be a vector that's parallel line? You got it. That's exactly what we're going to do. So let's find this parallel vector, the tip minus the tail. What would be a vector that's running parallel to that line? Parallel vector, oh you bet.
2,
It's on the line.
4.
And I can slide it anywhere off the line, but it would stay parallel to the line. 7 minus 5 is what? 1 minus -2?